Alright, so today we're going to take a look at hyperbolas. And first thing we should say about hyperbolas, because we've already done ellipses, is that they all have about the same parts. Okay? Where we have a center here, HK, an A, a B, and a C. And they're all basically meaning the same things as what we had from ellipses before. Right? Got the same stuff here. We've got an HK at the center, we've got an a B, and a C out to the focus. Okay, so as we go through this lesson, I'm just going to keep comparing to the similarities between the hyperbolas and the ellipses, just to kind of give you a background on what's going on. Okay, so when we look at the differences between the two definitions, a hyperbola is a set of points on a plane such that the difference of the distances to the two fixed points, the foci, is a given constant. So any point that I pick that's actually on my shape, the distance, there's a ruler here so we can draw this in nice, between the first focus and that point. So if we'll call this focus 1, and up here is our point, we'll call that xy. Okay, and our second focus, what the definition is telling us here is that PF1 minus PF2 is equal to 2a. Okay? And this looks really familiar to the equation of ellipse that we worked on. It's not quite the same, because here, the two distances, so here's focus 1 and focus 2, and we'll put a point out here someplace, doesn't matter where, okay? And we'll call that point P, which has an x and a y, okay? The distance between the focus and the point, the first focus and the point, and the second focus and the point, these two are add to give up the same number no matter where we are on our ellipse. Okay, so PF1 plus PF2, oops, P in there, okay, is going to equal whatever my 2a is. Okay, so it's the plus and the minus sign that makes a difference between an ellipse and a hyperbola. Okay, so not too much different to say here, except that when we're dealing with the ellipse, the distance between the center and this first vertex is going to be shorter than the distance from the vertex to the focus. Okay, so the C distance is actually longer than the A distance. All right. The other thing to note is that the orientation of the hyperbola, whether it's horizontal or vertical, doesn't depend so much on the bottom number, but the placement of the top variables, the x and the y. So if I've got a horizontal hyperbola, I'm going to see x first. Okay? And if I've got a vertical hyperbola, I'm going to see the y first. Okay? And I guess the other difference that we can kind of compare with the ellipse is that this looks really similar to before. I've got two terms equals to 1. But here in the ellipse, or sorry, in the hyperbola, it's a minus sign in between. Okay? Whereas before, with the ellipse, got the same setup here, except I've got the plus sign in between. Okay? So that's how in the equations, that we'll talk about it later, how we distinguish between an ellipse and a hyperbola. Right? Okay? So here, this is just the second one. It's a look at a vertical hyperbola, and all the same parts, except now I've got my A's going vertically along with my foci. Okay, and the last little difference that we should point out here, I suppose, is how to find C. Okay, so just like everything else with this, it's a little bit backwards as far as the sign here goes with ellipses. Here, C squared is going to equal A squared plus B squared. Okay, that's for the hyperbola. For the ellipse, it was c squared is equal to a squared minus b squared. All right. So that's enough chit chat about that. Let's actually try and graph a few of these, and we can learn as we go doing that. All right. Let's get this all set up here. There we go. Okay. So same as before, HK is my center. So the center of this one is going to be 2 and 3. So let's go 2 over, whoops, 2 over and 3 up. There's my center. And I guess before we get too carried away here, we should figure out what kind of ellipse we are dealing with, like a horizontal or a vertical one. So unlike the ellipse, we don't necessarily just look at the denominator of each term to figure it out. Okay? We just look at which term and which variable is with the term that's in the front, which one's positive, and which one's negative. So in this case, the x has the positive and the y has the negative, so I know that that's going to give me my horizontal ellipse. Okay, so now we'll go start looking for a few more points, and we'll start with A. A always goes with x in the hyperbola, so I know that this is a squared, so A here must be 3. Okay, so because it's a horizontal ellipse and I'm looking for A, I'm going to count over 1, 2, 3 in each direction from my center. Okay, likewise with B, so B squared is 25, so B must be 5. Okay, so go from our center, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay, and remember our formula, c squared is equal to a squared plus b squared now, and that's going to get us our c. So a squared, sorry, c squared is equal to a squared plus b squared. So c is equal to, c squared is equal to 34, so c is equal to the square root of 34. Okay, so square root of 34, we know it's going to be somewhere in between, well, pretty close to 6. Okay, so when we go to count here, I'm not going to bother putting in the decimal. We'll call that 34. And for the two foci, we're going to count 6 this way. So 1, 2, 3, 4, 5, 6, and a little less. Okay, and same here. 1, 2, 3, 4, 5, 6, and a little less. Okay, so what we'd like to do next is, well here, let's find what the foci really are. Okay, so we want 2 points there. Okay, so we know that the height of both of those points is going to be 3. Okay, and we know that both of those points are going to be in relation to the center. So our center point here was 2. So the point that's out here is going to be 2 plus this distance, our c, root of 34. Okay, and our second focus here is going to be that same distance, the opposite direction of a distance of root of 34. So 2 minus the square root of 34. Okay, and now we'll go take a look at our vertices. So minus 1 and 3. And over here it looks like 1, 2, 3, 4, 5. 5 and 3. Okay, now we want to actually draw the picture, and we need a little reference point. Like, we know that there's going to be 2 arms of our hyperbola that go like this through our focus, but I don't know if it's going to be deep like this or if it's going to be really narrow like this. So we're going to go back to our first page here. If you notice, there were a couple of lines that were here that it looks like our hyperbola is going to approach. Here's the hyperbola's asymptotes. Okay, so we're going to go and try and draw those asymptotes, and they form this little box. They go through the corners of this little box that are inside our hyperbola. Okay, so really, if you look at your hyperbola, we can kind of get at least an equation So our asymptotes are going to be the equation of a line, and I'm going to choose point slope form to fill in. Okay, and we already know a point in our center, so we can refine our formula here a little bit. So y minus, okay, hk, okay, and the slope is already inside of that box too, because I can see that the slope is going to be the rise over the run, or the b over the a. Okay, so this is a good way to find our asymptotes. So let's give that one a try. Let's move this over here. So y minus k is equal to b over a times x minus h. Now that's the formula you can remember to put in, but better just to kind of know that you're dealing with the equation of a line and that you're trying to find the slope, and you can find the slope in your b and your a. Okay, so let's go ahead and build our box, all right, that our asymptotes kind of follow through. So we're going to go here and draw nice, really fancy here with some pencil crayons. Okay, know that a line's going to be there through our A, extending up here through our two B's and our two A's. We get this nice little thing that sets up our asymptotes really nice. Okay, and we'll go find the equations in a second here. It's just nice to be able to see. Okay, I've got a distance of A from here to here, so I set up one of those lines at A, a vertical line at A, and I've got this distance from here to here is B, and I set up a horizontal line there. So it works out kind of nice. Okay, so that's where my asymptotes go through. Okay, so without even knowing the equation of the asymptotes, we can at least draw them. Okay, and be able to get a relatively good picture of what our hyperbola is without actually knowing the equation of the asymptotes of the hyperbola. Okay, so here's those two asymptotes. And now I can go and draw this hyperbola. Something like this. Okay. So it's the line that the hyperbola is going to approach, but not actually ever get to, as x gets really big and small. Okay, so there's a hyperbola. It's kind of ugly in here, but you get the idea. Okay. So now let's go and find the two equations for those. Right? And so I know that the center here was at 2 and 3. So I'm going to go y minus 3 is equal to, let's find the positive slope first. Okay, so the slope of this one, I already know it. It's 5 over 3. Okay, rise over run. So this distance right here, it's already in the box, right? So 5 over 3 times x minus 2. Sorry about that, kids. A little technical difficulty there, but we got through the second asymptote here, which we can see the slope for is, so we're looking at this line now, is going to be down 5 and over 3. So we're going to connect 2 points of the line, and that gives us y minus 3 is equal to minus 5 over 3 x minus 2. And that completes like a pretty good skeleton of what an ellipse looks like. I'm going to leave these two for you to try as homework for tonight. So yeah, give those a go and make sure you know what you're doing when you come to class next time. All right, cheers.